Hi, and welcome back to my channel. Today I'm going to be doing a COMSOL Multiphysics tutorial on thin film resistance. And this study is going to use the thin layer approximation, and it just goes into the model definition and kind of the background theory for why we can use this model. The exact domain description left and approximation right. The current flows from the base plate to the circular plate on the upper surface of the device. So there's a constant potential on this arc, the circular portion. Below describes the current balance in all three domains in the real sandwich structure. So del negative rho, sigma, represents the conductivity. Del V, which is the electric potential. The boundary conditions include a current inlet in the base plate of the device and a constant potential at the upper circular boundary. All other boundaries are insulated. Simplified model is based on the assumption that the components of the current density vector in the x and y directions are small, and that the dominating transport through the thin structure is obtained in the z direction. For the middle layer, this implies that you can approximate equation 1 by the one-dimensional equation, negative conductivity, del squared v, only in the z direction. So basically we've simplified this by removing the x and y solutions. So we're saying a change in voltage is minimal or negligible in the x and y, and we're only paying attention to the z delta, del squared, d squared. Okay, so this drastically simplifies that equation, and it's possible to solve this equation analytically if the potential is given at the lower and upper surfaces of the middle layer. So if we were, for instance, given at boundary baseline is voltage 1, and then top of the layer is voltage 2. You can integrate analytically to get voltage equals A times Z plus B, where A and B are integration constants. If you arbitrarily place Z equals 0 at the lower boundary of the middle layer, you get the constants A and B from the boundary equations in equations 3 and 4. So what we've done here is just replaced the analytical solution with the integration constants for these boundary values. So V1 becomes B, this integration constant, and V2 becomes A times delta plus V2 equals A times delta plus B. So this gives B equals V1 and A equals V2 minus V1 over delta, which we've done just by algebraically rearranging these equivalencies, which produces the resulting equation for the potential. Voltage equals V2 minus V1, the change in voltage, the delta voltage, but over the symbol delta, times Z plus V1. Current density is defined as J sub Z equals negative conductivity dV dC. And then combining equation 5 and 6 gives this final form, J sub Z equals negative sigma times difference in voltage over delta. So this symbol delta, I don't know that they defined it anywhere, but it means the distance or the length of the thin film. I don't see that they define that. Well, anyway, that's what it is. This symbol, delta, is the thickness of the thin layer in micrometers, whatever the units are. Okay, so we've got a J, a flux. A flux would be defined as something per area per time. Okay, in the thin film approximation, the potential is discontinuous at the film boundary. Use the contact impedance node on interior boundaries to model a thin layer of resistive material. The approximation presented in this example is not limited to direct current problems. You can also use it for modeling of diffusion, heat conduction, flow through porous media using Darcy's law, and other types of physics that the divergence of a gradient flux describes. Case in point, here is the potential distribution in the modeled device. So the left is the full model, computationally expensive, and the right is the thin film approximation. The comparison reveals an excellent agreement of the potential and current distribution despite that the middle film in the study is relatively thick. Model figure 3 shows a cross-section plot of the potential through the structure center for the full model and for the approximation. The plots show excellent agreement obtained between the two models. So this is what we're going to produce, showing the z-coordinate versus electric potential in volts. So your full 3D model is in blue and thin film approximation in green. Again, showing excellent agreement. So this is a pretty long tutorial. I'm probably going to have to come back to this because I've got to go. But let's go ahead and get it started so I can save it. So I'm going to create a model wizard, 3D model, go into the AC/DC drop-down menu and choose electric fields and currents, and then choose electric currents. Add and study. And we're going to do a stationary, so I'll select stationary here and click done. So now I'm going to save this as thin film resistance. All right. Next, we're going to create the geometry. In the geometry toolbar, click Work Plane. So I'm going to go to the Geometry tab and click Work Plane, this icon right here. In the settings, locate the plane definition section here, and in the z-coordinate text field, type 0.1. So we're setting the, and then we're doing unite objects, clear unite, and then show work plane. What we're going to do is view a horizontal plane at z equals 0.1 meters, or what is that, 10 centimeters. So we're 10 centimeters above datum and viewing that plane, which is just the top plane of this. Alright, so now we're going to create a new geometry. In the work plane toolbar, click circle. So we're going to click circle, and in the settings window for circle, locate size and shape. And the radius, type 0.6, located at YW is going to be 1 meter, and build all. Now we're going to build a square. We don't have to change anything, so just build all. So now we have a square overlapping our circle. If you hit zoom extents, you can see. So in the work plane, click booleans and partitions and choose intersection. Control Alt to select both objects, or you can just click on them and then build all. Well, that's not right. Okay, I see. So we had to first build the intersection, and then we build another square on top of it. Now we're going to extrude this two-dimensional geometry into the 3 dimensions. And the Model Builder window under Component 1, Geometry 1, right-click, Extruding just takes your two-dimensional object and sort of lifts it out of the plane. If it were in the XY plane as it is here, then we're going to extrude it straight up into the Z dimension. You could also revolve about an axis. So you could say, let's see, if you had a line and you wanted to revolve about the x-axis, then you would end up with a cylinder. You can use these options for different types of geometries to make it a little simpler. Okay, so extrude, choose the object WP1SQ2 and then choose block. Okay, so I didn't actually have to hit build selected because when you choose the next thing, it automatically does that action. So now you can see the extrusion of our plane geometry down into the z-axis. Okay, so now I've got block selected. I'm going to go to size and shape, and the height text field type 0.1. Locate the position in the z text field type negative 0.1. Okay, so it's got a height of 10 centimeters and it's located at z equals negative 10 centimeters. Copy the above geometry and build the geometry for the full 3D model. Alright, so here's our second layer. And this would be neglecting the this is using the thin film approximation, so we don't actually build it. We don't build the sandwiched layer. In the geometry toolbar, click transforms, this wheel with arrows looking at icon, and choose copy. So let's see, I'm looking for that icon, transforms, copy. Click in the graphics window and then press Ctrl A to select all objects. In the settings window for copy, locate the displacement section. And we're going to place this at x equals 1.5 and y equals negative 1. Alright. And then move 1 in the geometry toolbar, click transforms and move. So again, going under transforms, move. And now we're going to select the object block 1 only. So the bottom one is block 1. In the settings window for move, locate displacements. And in Z text field type, Z equals negative 0.02. So we're just moving it down by 2 centimeters for our real model, which will have a 2 centimeter thin layer. In the geometry toolbar, click block. I'm going to go ahead and hit the zoom extend so you can see what we did. With the copy, we copied the whole thing, and then with the move, we basically did a copy and paste, but the move operation did the paste offset, so we can see both of them beside each other. Alright, so I clicked on block again, and in the height text field type 0.02. So here's our thin film for the real model. So now you can see it in there. And build all objects. Alright, click the zoom extents button, and now the geometry, the thin film approximation, and the full 3D model should look as in the figure below. So here's our full 3D model. That doesn't look right. Something's not right here. Oh, position. So I put the height of the thin layer as 2 centimeters, but I didn't change the height to negative 0.02. Okay, there we go. Next, we're going to actually be putting in the physics, so the electric currents module. In the model builder window, under component 1, electric currents EC, click current conservation 1. this top condition right here. So you'll notice a pattern as we're going through these tutorials. Like in my last tutorial, we went through the Navier-Stokes equation and how to sort of analyze the base equation and see how many boundary conditions in each dimension, and if you need any initial values in the partial differential equation for the governing equation. You can see by that analysis what types of conditions should be here. But just by importing certain physics modules, you'll see that some of them appear by default. So for instance, initial values will always appear if you have a stationary problem, for instance. And in this case, we've got boundary conditions that we'll need to know, or we'll need to fill in some conditions for: current conservation and electrical insulation. So if you right-click on electric currents, you can see all these conditions to choose from. And you can also see these from physics, domains, boundaries, pairs, edges, etc. So some of this will be a given for the model, so you know automatically that you need these three conditions. But if there's any additional unique characteristics of your model, then you can add those boundary conditions in. For example, asymmetry condition or distributed impedance. So right now, we're going to be modifying current conservation 1. In the settings window for current conservation, locate the constitutive relation JCE section. So right here, from the sigma list, choose user defined. So we're changing from material to user defined. And you'll see the field appears where we have to enter sigma, the conductivity, and units of Siemens per meter, and an associated text field type 1. So our unknown material has an electrical conductivity of 1 Siemens per meter. Now we're going to set the normal current density 1. In the physics toolbar, click boundaries. So I've already got the physics tab up here selected. Now I'm going to select boundaries drop down menu and choose normal current density. Select boundaries 3 and 20. Let's go to layers 3 and 20. And in the settings window for normal current density, locate the normal current density section right here. And for JN, J sub n text field type 0.3. All right, the next section is ground 1. In the physics toolbar, click boundaries and choose ground. So ground is the first one in the listing under electric currents. And then you'll see the ground condition appear in our list. Choose boundaries 11 and 25, top layer, 11 and 25. I'm going to add a contact impedance 1 boundary. So once again, going to the physics boundaries and now selecting contact impedance 1. Click the wireframe rendering, which I'd already done before, and select boundary 23 only. Let's see. 23 is going to be the in-between layer, or the interface of the contact impedance layer. So I'm going to select the full 3D model and remove those contact layers. And when I went to select the boundaries and I didn't know exactly what I was looking for, I did Control All, but instead of selecting all boundaries in the entire model, I only selected the boundaries that might potentially be feasible for this boundary condition. So you couldn't have a contact impedance boundary condition anywhere except at an in-between contact. So you can see it's pretty smart. I mean, it's honestly hard to mess up unless you're putting in information that's not representative of your physical problem. Okay, so I'm going to remove the full 3D model once, and I'm going to have to take a break, and I am back. So we left off at current conservation 2. So I'm going to click in the physics toolbar and click domains and choose current conservation and then domain 2 only, which is going to be the thin layer in the 3D full model. In the settings window for current conservation, locate the constitutive, I don't know how you say that. Constitutive sounds right. Relation JCE section, and from the sigma list, choose user defined. And the associated text field type 0.1. So we're saying this thin interfacial layer has an electrical conductivity of 0.1 Siemens per meter. 0.01. Oh, good thing I looked at that. That was off. And now we're ready to study. So I'm going to go up to the Study tab. In the Model Builder window, click Study 1. Oh, okay, so you can either select the Study tab or Study in the Model Builder window and hit Compute. Oh, wait, no. Cancel. It said clear the Generate Default Plots checkbox because you will add the desired plots manually. Okay. So we're unclicking this one and now compute. And let's see, we just have to do a little bit of plot manipulation and that'll be it. Okay, so under results, we're going to reproduce the volume plot of the potential from figure 2. 3D plot group 1. In the home toolbar, click add plot group. So I'm going to click home, add plot group, and choose 3D plot group. Right click 3D plot group 1. So now I'm here in the model build window, right clicking and choosing volume. And in the settings window, locate coloring and style section down here. Clear the color legend checkbox. I'm checking. And in the 3D plot group 1 toolbar, click plot. All right. Okay, interesting. Haha. All right, that was it. It was a units issue. Okay, so we solved the problem. It was a millimeters versus meters issue. Okay, so there is our volume plot that's been corrected. Now I'm going to update the line plots. To be z-axis. Okay, so if we go into the x-axis data, we change this to expression, replace expression z-coordinate. Alright, and the same thing for graph 2, which you wouldn't have to do if you had copied and pasted it. Alright, there we go. Now we're looking good. Alright, so there you have it. It took me a while to get there. I think it's better if I just go through beginning to end without a break, because then I don't make as many mistakes. But this was a fun little tutorial demonstrating COMSOL's ability to easily model and visualize data for both the 3D full model and a thin film approximation. So once again, if you zoom in, you can see here that we modeled the full 3D model on the left here with the 2 centimeter film in the middle. And on the right, we have the thin film approximation, which approximates a infinitesimally thin film in between two thicker layers. All right, so here we go. So that was it for today's tutorial. And if you're interested in more COMSOL tutorials, please like this video, comment, and subscribe. See you next time.